Hi guys, we're going to continue with chapter 5 which deals with relationships within triangles. The last lesson we were speaking about the mid-segment. In this section we're going to speak about perpendicular and angle bisectors. Remember, perpendicular bisector is a bisector of a segment. So really quickly I'm going to show you. If we have a perpendicular bisector, we would know that in a figure, if let's say this line were the perpendicular bisector of segment AB, I would only know that if I know that segment AB is not only cut into two congruent parts, but if it's bisected at a 90-degree angle. Now let's say we have this section here, C. Let's say I have a point C on my perpendicular bisector. Well, this point, I know that I can attach and make a triangle. And remember, in the last chapter, we were dealing a lot with triangles and proving them congruent. These two triangles that are made up, so triangle AC, and let's call this point D here, and BCD, we know that they're both congruent because, since this segment here is congruent to itself, they're congruent by SAS, okay? Which means then, using the CPCTC we've mentioned in class, the corresponding parts of congruent triangles, we know that AC is congruent from BC. What does that mean? That this point C is the same distance from A and from B, right? So that's why I put here the definition of an equidistant, really should say point here, is a point that is the same distance from an object. So this point here, C, is the same distance from A and the same distance from B, which brings us to theorem 5-2, the perpendicular bisector theorem. So this theorem states that if a point is on a perpendicular bisector, so let's say we have point P here. If a point is on a perpendicular bisector, then that point is equidistant from the endpoints of the segment. Okay, so as an if-then statement, we can say if a point is on the perpendicular bisector, meaning if line PM is perpendicular to segment AB, it's a perpendicular, but it's a bisector, so AM is congruent to BM, then, or I guess we can say congruent or equal, doesn't matter. Then we can say that it is equidistant. So AP equals BP, meaning that AP and PB, we know that this is also congruent because P is a point on my perpendicular bisector, okay? And the converse would say the opposite. So if I have a point, I'll write this one out actually. If a point is equidistant to the endpoint of a segment, then that point is on the perpendicular bisector. So I'm just going to put perpendicular bisector here. So the if-then statements would switch. So if AP equals BP, then everything that we have here, okay? Then that means it is a perpendicular bisector. Bisector. Notice here I made a mistake. Oh no, that's correct. So this is segment. And perpendicular we have here bisector. So AM is congruent to BM. Okay? So now that we learned these theorems, how do we put it into practice? How is it useful? Well, here we have a triangle. We have triangle ABC. and we have a segment going through it. What's special about this segment, BD? Well, BD is the perpendicular bisector of this side here. How do I know that? Well, it's perpendicular, and we know it's being bisected because it's broken up into two congruent segments. Well, we just said if a point is on the perpendicular bisector, we have point B, that's on my points B and D, but point B is on my perpendicular bisector of AC, right? AC is being bisected. That means that point B is equidistant from the endpoint. What is the endpoint of the segment being bisected? A and C. That means that BA and BC are congruent because of the perpendicular bisector theorem. If they're congruent, we know the measure is equal. So if BA equals BC, I can say that 4x equals 6x minus 10. And I know how to solve for x, right? Let's bring this negative 6x over. We're going to get negative 2x equals negative 10. Divide by negative 2 on both sides. So we get that x equals 5. But we haven't answered the question yet. This was a step. We found x, but they're asking us to find AB. So we're going to plug back into the expression for AB. AB equals 4x, which means that it equals 4 times what we found x to be, 5. AB equals 20. Okay? So this is how we put the perpendicular bisector theorem into practice. Another example that uses this theorem is problem 2. I cannot draw the figure that you guys have in your book for problem 2, but I can explain it. So essentially what they're asking for, what they want to do is they want to build a t-shirt stand that is the same distance, equidistant from rolling coaster and spaceship's chute. So if we make a segment from them, I don't have the right tools for construction, so I will rely mainly on explanation. We said that if a point is on the perpendicular bisector of this segment, then that point is equidistant to the endpoint. Meaning, all I have to do is find the perpendicular bisector. I know how to do that with a compass. I'm going to pretend that I have a compass. With a compass one way, with a compass the other way. This line right here connecting those 2 points would be my perpendicular bisector. Well, a point on that line, any point on that line is equidistant to my